What happens if you have something like this, and you want to find out if something like this is inside? Obviously you can't tell just by looking at it, but if you separate things out, the answer becomes clear. Scientists have the same problem. How do you know if there was once water on Mars? Or, for that matter, life? Obviously you can't tell just by looking at pictures of Mars, but scientists think the answer may lie hidden in tiny molecules in Martian soil. So how do you take apart a molecule to see what's inside? Luckily, scientists have a tool to do just that. It's called a mass spectrometer, and it lets us take an extremely close look at whatever we're studying. And even though Mars immediately comes to mind, mass spectrometers are used in multiple NASA missions. They're also used in labs for hundreds of scientific purposes. But the important question is, how does it work? Today we'll be looking at a special kind of spectrometer called the quadrupole mass spectrometer. It's called this because of the 4 long poles that make up the center of the instrument. So say you have a sample that's been turned into a gas, and you want to find out if it contains certain things. The gas is sent into the mass spectrometer, first hitting a piece called the ion source. Here, a stream of electrons hits the molecule, breaking it into fragments and giving each fragment a charge. Next, the fragments enter what's called the analyzer. Here, they're separated based on their mass, and the analyzer is tuned so that only the fragments we want to see make it all the way through. Everything else flies off in a different direction. After this, the fragments hit what's called the detector, and scientists record the data. If you're looking for more than one kind, the analyzer can scan across a range of fragments, building up a record of not only what kind, but how many. Once you have these results, called a mass spectrum, you can verify that your sample in fact contains what you're looking for. And here, the real work begins. The mass spectrometer is a powerful tool, and by taking many samples, looking at the results, and studying what we find, scientists can work to discover not only the secrets of water and life on Mars, but also answers to bigger questions about the universe. And all by studying something as tiny as a molecule.
We want to know, has life ever existed on Mars? Do pockets of life persist on Mars today? NASA's approach to answering these questions is to break them down into smaller and smaller steps. First, we need to know if ancient Mars was habitable. Did it once have the right climate and the right chemistry to support life? The Curiosity rover is investigating these questions by looking for organic molecules containing carbon. Organic molecules are the backbone of all life on Earth, though they can also come from non-living sources. Today, the surface of Mars readily destroys organics, making them difficult to detect.
We are decelerating.
6 years ago, Curiosity landed in Gale Crater on an ancient lake bed. A few months after arrival, it drilled into sedimentary rocks and detected traces of organic molecules using an instrument called SAM. Now Curiosity is climbing the mound in the middle of Gale Crater, and SAM has made a subsequent detection of organics. This new detection is exciting because it comes from rocks that are billions of years old. That means that the organic material within them is extremely ancient. Some of the organics that SAM has detected contain sulfur, likely introduced through geological processes. Sulfur can act as a preservative, binding organic molecules together to make them tougher and protecting them from oxidation. In fact, sulfur is the element that makes hair and fingernails tough, as well as vulcanized rubber. Martian sulfur has probably had a similar effect on these old organic molecules, helping to preserve them over geological timescales. SAM made the new detections by heating samples of crushed rock to very high temperatures, above 1,000 degrees Fahrenheit. This vaporized the samples and released several species of small hydrocarbons like benzene and propane. Because the hydrocarbons were released at such high temperatures, they may be the fragments of bigger, heavier molecules within the rock similar to kerogens. On Earth, kerogens are found in rocks like black shale and coal and are the products of ancient plant and bacteria. We don't know if the recently discovered organics on Mars are of biological origin, but it's exciting to find such old material preserved right at the surface. This finding is also encouraging for future exploration. In the distant past, Mars was much warmer and wetter than it is today. The rocks at Gale Crater tell us it was once an environment where life as we know it could have survived. The discovery of ancient organic molecules shows that another ingredient of life was present at that time, and it broadens our understanding of habitability of both ancient and modern Mars.